Hi and welcome along to another physics video. Bit of eccentricity today. We're going to try and explore the subject of phase. And hopefully what you're seeing now is a shadow, and that shadow is moving in the way that one point on a wave would move. Later on we'll call this simple harmonic motion. So how are we achieving this motion? Well, if I kind of move you round a bit, you'll see what I managed to find an old-fashioned record player. This is what we used a couple of generations before Spotify. A little spice pot, and then behind me whirring away you can hear a slide projector. And now when we've only got one object we can't really do phase, so I need to just stop it and add a second object to join the somewhat depleted jar of ground ginger. So let's have a look. So I've got a little empty packet of garam masala. I went for a smaller packet because now the shadows look different, don't they? So let's set it in motion again. So if we just focus on the two shadows, you would say that those are completely out of phase. When one reaches maximum displacement to the left, the other one reaches maximum displacement to the right. So let's have a look and see how that looks from above. Well, the reason why the two shadows are completely out of phase is because the objects are on either side of the disc. So the concept we're trying to work on in this video is that there is a relationship between the placement on this disc, which in this case is in the real world, but in an actual wave or an actual oscillator is just an imaginary concept that helps us work out what's going on. If I just pause it for a moment, we're just going to look at the angle between these two objects. And the angle between the two objects on the disc is pi radians, isn't it? So when two things are completely out of phase, we call that a phase difference of pi radians, because on our imaginary disc, that's the angle between the two things. We're now going to set them so they're at right angles to each other on the disc. So the phase difference is now pi by 2 radians. Surprisingly difficult to write and video at the same time while you're holding the camera. And when we set that in motion, you can see, first of all, looking here, the small container leads the large container, and you can see that in the shadow. The small container all the way left, then the large container. Small container all the way right, then the large container. So in this case, the phase relationship is the small container leads the large container by pi by 2 radians. And because it's a complete circle, we could of course say the opposite, that the large container leads the small container by 1.5 pi radians, measuring the angle round the other way, but I guess that makes less sense. We can show completely in phase where the two objects are on the same side of the disc. So you can either say now that we have 0 pi radians between them, or you could say 2 pi. That would be exactly the same thing there. They're on the same location in the disc, and it will work for any arbitrary angle between them. Okay, so let's make doesn't matter what that angle is. We see a more complicated phase relationship on the screen. If we wanted to describe that in some accurate way, we would measure we would stop the record player turning, draw lines out to our two objects, measure the angle between the two in radians, and then that's the phase angle in radians. Okay, just going to formalise what you should know about phase then at this point. So what we've seen is that if the phase relationship between two objects is pi radians, then they are out of phase. That's my luck. They're out of phase. 2 pi or 0 is in phase, and then pi by 2 was 1/4 of a cycle. And I'm just going to now relate that to 2 points on a wave. So let's draw a wave. So if we imagine these 2 points on the wave here, here and here, which are of course in this picture one wavelength apart, then we can say if the distance between the 2 points, and of course this would apply to the path difference as well, then the phase difference is pi radians. And those two quantities, 2 pi radians, sorry, just like we were saying out there, they're in phase, so we're going to call that 2 pi radians. If these 2 points were like these 2 points, that point there and that point there, which are half a wavelength apart, then the phase difference is half, so it's pi. So if the path difference, or the distance between the 2 points of the wave, is 1/4 of a wavelength, then the phase difference is pi by 2 radians. And you can just use that proportionality to make any relationship you like between phase and path difference. If we have a path difference that's more than a wavelength, so let's imagine we were asked to consider what is the phase difference between this point here and this point here, and that distance there is 1.5 wavelengths, or 3/2 lambda, then we just knock off all the whole wavelengths. So that just comes back to exactly the same phase difference. So if it was half a wavelength, which is pi radians, and even if it was something extreme, and I have seen this like 48 pi plus pi by 2, then again you can just ignore the 48 pi because that's simply 24 full cycles. Okay, thank you very much.